All right, hello. Um, Today I'm just gonna show you how you do the EVM puzzles for Ethereum. So basically, it's a set of EVM puzzles that are out there. There, at least as I know, two different sets. There could be more, but these are basically ways to get really familiar with how the EVM works under the hood. So the EVM is the Ethereum Virtual Machine. And the EVM is what is run when you send a transaction to the miner. So let's say you want to send some Ethereum to someone, you want to send some DAI to someone, whatever you have, or you want to modify the state of a smart contract in whatever way you can think of. So in this case, you need to sign a transaction, you need to send the transaction basically saying what you want to do. You need to send value with it, ether, etc., and if necessary, and you send this to the nodes, right? Sometimes or often you do it through MetaMask. So MetaMask is actually on the back end connected to most likely like third party like tools like Alchemy and Fura, or they're running their own node. I mean, and this is how in general it works. You can also run your own node, but the point is that you need to send this message to a node, and this node will then kind of take apart your transaction to just verify that you were the one that sent it, verify you have the gas necessary to execute it, and so on. So just some verification steps, which is also why it costs at least 21,000 gas to make a transaction. All these checks have to be made. Now, once they've been made, then the node will basically send the transaction out to the network if it's something that modifies the state, and basically it'll be mined and included in the next block. If it's just a view call, like you're just looking for some data from the network, typically the node itself will be able to handle that and just give you the data right back, aka it's not a state-changing transaction, right? Okay, so the point is just that when the node receives your transaction is telling it to do something. So what it'll do is it'll open an EVM, a virtual machine, and all state changes to Ethereum, to the underlying contracts and everything, is done through this virtual machine. So we're basically restricting what can be done through a set of so-called opcodes, and these opcodes are basically going to be run by this machine. So this can be add these numbers together, change the balance of this account, and so on. There are different opcodes in this stack-based virtual machine that are being run. So it's just a very short kind of view at what happens. It's way more detailed, but just understand that at the end of the day, you send a transaction, a virtual machine is spun up, and the virtual machine will just go through opcodes that are included in the transaction data you sent, and then execute that. And if all goes well, it'll actually change the underlying state, and that's it. If it fails, it'll just roll back to a previous snapshot of the state, right? Of this global machine state. So, all right. So what we're gonna do is basically take a look at these opcodes. A really good way to get familiar with them is definitely watch some videos on what the Ethereum virtual machine is. I'll post some links, and and then we're gonna take a look at just like kind of how we can get more familiar with them. So I'll show you all that. Make sure you like this video and subscribe if you like more content, and if you like this kind of content. This is more advanced Solidity in general I cover, but I can also do some more kind of simplifying tutorials and so on. So yeah, just let me know what you'd like to see. So like and subscribe, and yeah, let's get started. All right, so here we are gonna jump in to some code, but first I just want to show you where you can go and fetch this code. So this does live on GitHub. It's called EVM Puzzles. Okay, is the name of it. So you can go here. I'll post a link, but this is a link up here. Go and clone this. Okay, so you can clone that. So here I'm going to open my terminal, and I'm just going to go ahead and clone that repo. So there you go. Now we can CD into the EVM Puzzles. Okay, so we're there. So how do we actually... what is this about? What is this EVM Puzzles about even? Well, now we cloned it. Let's follow the instructions. It says clone this repo and install its dependencies with yarn. So we're going to type yarn. That installs everything for us. Just give that a second. In the meantime, let's keep reading. And then it says run npx hardhat play, and the game will start. All right. Then they also say you can use EVM.code's reference and playground to work through this. Great. So let's click that. That's actually a really good help, because if you go to this link, I will also be posting that. It is EVM.codes. And what you see here is a bunch of instructions. These are the opcodes. So you see the opcode 00, 01, 02. Okay, so that's what the actual opcode is that sits on the stack. And then the name, there's just some mnemonic here, so stop, add, multiply, subtract, and so on. And then the minimum gas that it will cost to run that operation. And you can also see what it takes in from the stack. So the stack is this, I don't know if you're familiar with the stack, but you can think of it as like a stack of plates. You can only put a plate on top, and you have to take off the top because you can't get access to anything in between. Okay, so it's like you can put plates on top. So you imagine here that it takes input. This add command takes two inputs. The top plate and the second top plate. Okay, so it takes these two plates, and they can be whatever they are, A and B. They can be 2 and 4 in value, whatever it is, right? And then what it outputs is A plus B. So what they mean here by stack output is that this operation takes these two plates off the stack, does something, in this case adds them, and then it does put a plate back with the added result. That's what this means. You can see some of them don't put something back on the stack and don't even take an input. Okay, so it's important you understand that some of them don't. So for example, call data copy, you see this opcode 37. It takes three plates off the stack, but it doesn't put a plate back on the stack. So just be aware of that. Okay, it even describes it here. So all of these, when you click them, they'll expand, and you can see that index 1 is top of stack. So that's the first plate as you start to take off plates. So it says A is the first plate on this stack. This is the first thing you take off the stack. B is the second one. So it returns A plus B. That can be important when the order matters, right? Like you need to know exactly which plate. And they give you an example. And you can even jump right into reproduce this in the playground. So they have this playground as well. You see at the top. You can click there and post any opcodes you want or mnemonic. You can see you can post different things, even Solidity, Yule. And what you can do is basically click run. So now they have auto-populated this to give an example of addition. When I click run, and we're going to be doing that more as we go through the puzzles. But now, this is not the puzzle. This is just clicking. This is just seeing how this add operation works. So when I click run, I can send in some call data. I'm not going to do that, but I can send in some call data. This is call data that has to be written in hex. So 0x something in hex characters. So 0 through F, which is basically 16 values. And then value to send. Value to send is how much way, or you can change this to ether or whatever you want to send when you click run. We're not going to do that. We're not going to send call data. We're not going to send any value. We'll just click run. So we already did that to the right. You see that the total gas used so far, and we just got started, is 21,000. That's what I was just saying. So whenever you do a transaction, whenever you do that in Ethereum, it costs 21,000. And that is because the node needs to verify that your transaction is valid. It'll cost them money. They need to make sure that the sender is associated with the signature that was made in the transaction. They need to make sure there's gas enough. They need to make sure, all kinds of things. Okay. For example, that the nonce of your account is basically makes sense. If it doesn't, you can do replay attacks and stuff. So there's like this nonce associated with the account that ticks up every time you send a transaction. Things like that. There are more things, but things like that. And then the current gas is basically this push. Okay, so basically this is the location, the code on the left here. So this is basically, you can think about this as like the size of the code essentially. Basically this is 28 plus 1 because you have this 0, 0. And then the push operation, we're going to push 0A on the stack is what this says. Okay, so anyway, so we click run. The way you step through these opcodes is over here. Right now we're hovering over this very first opcode. Nothing has been done yet. You see below, before we're going to step, you see below, you see the memory. This is how memory looks right now. Memory is just a long array in Ethereum. You see the stack. The stack is also, like I said, it's just kind of a stack of plates. It's size 1024. It has 1,024 elements, and it's just, you can think of it as like an array. Okay? That's a very simplified way of looking at it, but my point is just that it can go to 1,024. Okay. Now, it doesn't mean that any opcode can have access to the entire stack like that. So that's why I just kind of It's just a simplified way of looking at it. But anyway, the storage is interesting. That's very unique. That is not just a long array in Ethereum. It is more like a key. It is more like a mapping, like a key value thing. So each slot will map to something. So there's like a key, slot 0, slot 1, slot 2, and then the value, whatever is stored there. And it's, in essence, that is because of, essentially dynamic arrays, how they handle that, and so on. So it's too complicated to discuss right now, but that's just the structure of it. But we can see how storage looks. And the return value is basically just when we call return from this. Now, there's no return right here, but we could add a return opcode, and it would just show us what the return value is. So that's how you interpret this below. Let's walk through. When I click step now, it will actually execute this command, which is telling us to push 1. What does that mean? It means push 1 byte. And to the right, this means we have 1 byte. And indeed we do, because 2 hex characters, 0 and A, combined is 1 byte. 1 hex character is 4 bits, half a byte. Okay, so we put 0A there. A in hex is 10 in decimal. But anyway, so what's going to happen here is we're going to put this byte on the stack. So we will notice below, when I click this, 0A will go on the stack. So I'm going to click, and it does. So A goes, now 0A, like A is just a shorthand for 0A. Okay, 0 doesn't do anything, but that goes on the stack. Okay. In reality, kind of to expand a little bit on that, the full word, the full 32-bit, or 32 bytes rather, is kind of what goes there, and has just a lot of leading zeros, but they're not showing that here. Just to be clear. Then they do a push 1 again on 0A, so another A will go on the stack. Notice how another plate has entered on top of the previous plate, and this is the top of the stack. This is the top plate. So we can't access the bottom plate without first removing the top plate, is kind of the point I want to make here. You can't just jump around in the stack as you like. As opposed to memory, you can jump around as you like, and storage technically also, as long as you know what you want to access. Okay, so we can now add. Now we're going to call the add command. Remember, the add command takes off 2 plates from the stack and it puts on the sum back onto the stack. So in one operation, you'll see these 2 A's disappear and the sum reappear on the stack. And it's going to go so fast that you'll just see the sum as 1 element on the stack, as 1 plate on the stack. Okay, so 10 plus 10 is 20, but it'll be represented in hex. Okay, there you go. So that's 14. Okay, good. And okay, so yeah, so how can you just quickly verify? Well, notice that 14, it has the second placeholder, if you will, right? Is like in decimal, that's like the 10 basically, right? Like each time you move a decimal, you kind of go up another factor of 10. Here, because there's 16 like characters in the hex alphabet, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. The first one here, this 1 actually represents 16. So this 1 means that this value 14 in decimal is at least 16, and then you got to add the next to it, which is just, since that's below 10, it's just the same as decimal, so that's 4. So this says 16 plus 4, that's 20. Okay, that's how the stack looks, and it put it right back on the stack. Now we only have 1 plate. Great. Now the next command says push 32 bytes. Before it was 1 byte. So 32 bytes, we should expect, pretty much 64 of these. And these are just all Fs. Basically, F behind the scene is just 4, like 1 F is just 4 ones. Okay, so that's how that's like the largest, like with 4 bits, that's the largest value you can have, is just 4 ones. Right? And that's what an F is. And so we're going to push that on the stack. So it's going to look like this now. Look at that. The whole thing went on the stack. That's great. That's the full like 32 bytes, like I mentioned earlier, that can be on the stack. So technically, again, when the A was there, it was like 0, 0, 0, A, right? Like 31 zeros before it. Anyway, they didn't show that. But okay, now push 1. I'm just going to push 1. So now we have 1. We have all these Fs. We're going to add those together. And we're going to see what we get. So obviously this is basically the largest value you can have. And then we're going to add 1 to it. And there you go. It's going to give us 0. Okay? That's because of the overflow. But all right. So cool. that's it. These are 2 examples of adding. Now, okay, great. We're going to make it much more complicated, but I just want to get you, like, feel free to go to evm.codes, go to the playground, go into these opcodes, open up an opcode, say reproduce in playground, and you can kind of see how they all work. Okay? It's a great way to just get an intuition for it. There's definitely some more advanced ones. The add is obviously easy. There is there's basically a create statement. There's a call. You can also search here, right? So you can say create. This is basically creating a new contract. So you need to, what does it take as input? It takes the value and weight to send to this new account you're creating. It takes a byte offset in memory, in bytes, the initialization code for the new account. So you need to also create the initialization code and so on. Much more complicated topic. We're not going to cover it here, but that's, just to give you an idea that these opcodes can get pretty complex. It's not just adding and subtracting. They can create, they can call other functions, things like that. Great. Now back to our game. So now that you know what opcodes are, they're just these like instructions here in the playground. Now that we know what they are, basically what we're going to have to do. So actually, let me show you because I didn't do that before. This to the right, we just stepped through. Great. Notice to the left, before this was written in mnemonic. In fact, it resets every time I do this. But anyway, now I just click run. So this to the right matches this to the left. The point is, this to the left is in bytecode. This is just important because as we go into the game, they're only going to show us the bytecodes here. And then so this is 60. So what does this 60 mean? So by the way, you always know the opcodes are like 2 digits or 2 characters, like hex characters. So you know that 60 is 1 in 1. Okay, so the way you figure that out is you go to the opcodes and you just search for 60. So you can have 2 of these up next to each other, right? So you don't have to jump back and forth. And it just means push 1. That's what 60 means. Okay, so go back to the playground. That's what 60 means. Push what? Push 1 byte. Okay, what are you pushing? 42. You see that to the right over here? It says push 1, 42. That's exactly what it said. And then 60, well, now you know that means push 1. Okay, what are you pushing? 0. Okay, let's confirm. Yes, push 1, 0. And then 52 is memstore, like mstore, so that means put that in memory. Let's actually run this just to see the memory being stored. So we're going to push 42, we're going to push 0. What is mstore? Well, let's figure it out. We can duplicate this tab, we can go to the opcodes, we can go to mstore, which is 52, right here. And what does it take off the stack? It takes the top plate is the offset in memory in bytes, and 2 is the value to write in memory. This is the 32 byte value to write in memory. What is offset? It just means when you tell it to store something in memory, the computer is going to ask you, great, I can definitely go and store this in memory. You just need to tell me where. Because there could be a lot of stuff in memory. So where do you want this stuff? Because if you just tell me wherever you want, I'm not going to know. So that's the offset, right? So if you have already stored stuff up to a certain location, obviously you're going to give that location so that it stores the next stuff after that, right? And then the value obviously is what to store. Okay, cool. So anyway, so it says here the offset is the first one. So it's just going to store it in 0. We don't have anything in memory, so the offset is 0. And it's just going to store 42. Oh, I clicked run. There you go. Cool. So it stores 42. Now notice in memory how it actually does show us the full 32 bytes, just to make that clear. Not on the stack. And then we're going to push 20, we're going to push 0, and we're going to return. So what's the return? Well, you jump over here again, and you look at return. Now, of course, you can also see that over here, it's going to be F3. But look at this, F3, right? This is the return. So you can kind of match the two. All right, so if we look at return, we can go look at return right here. And that takes the offset, byte offset in memory to copy that will be return data. So it's going to return data when it returns. You need to tell it, or it will ask you, like, where, sure, I can return some data, but where do I go find that data? You tell it, oh, by the way, that data you need to return, it has this offset in memory, just like we just talked about. You need to tell it where. And the other one is the byte size to copy. So that's how much to copy starting from that offset. Okay, so together with an offset and a size, well, you have a chunk of memory and you're returning that to the caller. That's what return is about. So that's what's happening here. Boom. And then you see that the return data is 42. Okay, because you said the offset is 0, you're returning 20 in hex, which is 32 in decimal. So that's all of these 32 bytes. And that's what's returned right here. Okay, so that's how it works. All right, I think now we're ready. Let's jump over. Let's start playing here. So npx hard hat play. That's what they told us to type. So we're gonna do that. Oh, okay. It's gonna present us with puzzle 1. So puzzle 1 looks like this. These are the opcodes in the middle column. 34 that maps to call value. We can go and verify that in evm.opcodes there. 56 is a jump statement. And FD is a revert. Another FD, and so on. So there are multiple reverts here. And then a 5B is the code for a jump destination. A jump destination is a special opcode that just tells the compiler that, hey, if someone just jumped here using a jump statement, for example, this one, if someone arrived here, it can only have happened if they originated from a jump statement. Okay, so you can ask, why would they ever get there through other means? I don't know. Maybe there's something wrong with the code. That's the whole point. If you somehow got here without jumping, well, that's bad. So you should revert and halt and panic. So that's what it does. So, but you can jump there. And then, yeah, the stop just ends the program. The goal of these puzzles is to get to the stop location. So you can say, well, what do you mean? What do you mean you need to get to the stop location? Because, like, what do you mean? Okay, so let's dive in. Well, it tells us enter a value to send. Okay, a value, again, just like over here, the value they're talking about is this value to send. So it's something in way. It's a number in way. So let's start by sending 0. Okay, I just want to show you and kind of show you what happens. Call value is a special opcode that takes the value you send in and it puts it on the stack. So call value will be 0 when I send in 0. It'll be 1 now. It'll be 2, 3, 4, and so on. That's what call value is. And you can confirm that in the EVM opcodes. That's where we can... So you'll be using this a lot. But this is why it gives you a good intuition of what these codes are. So the value of the current call in way, you see that is the top of the stack. So when we send in the value, this 4 will be put on the stack. This will just happen behind the scenes. It'll be put on the stack. And then call value... Oh, sorry. The call value will be the call value, I should say. Okay, like I'm talking about this value now. This call value opcode will put it on the stack. Okay, that's what I meant to say. So that will put the 4 on the stack like a plate. And then the jump, let's go see what jump does. Okay, so this is how you do these puzzles. You just you have to understand just like what happens in the beginning there and what they're, how you can get to the green point down here, how you can get to stop. And I'll show you how not to get there and how to get there. Okay, so jump. What does it take? It takes the counter off of the stack, which is the byte offset in the deploy code where execution will continue from. Must be a jump destination instruction. Okay, so what this means is it goes look at this, like this jump opcode alone. It goes to look at the stack. It looks at the top plate and it says, what's the value of u? Okay, if the top plate says, oh, I have a value of like 0.4, right? Kind of like what we're trying to send in here, which is also just 4. Then jump says, great, I'll jump to location 4 in the code. Location 4 in the code is right here. How did I find that? Look at the left column. This is 4. Okay? So the jump will go to the hex location of whatever you specify. So if you specify 4 and jump, if 4 is at the top of the stack, jump comes along, it'll pull 4 off the stack and it'll jump to location 4 in the code, which is here. Cool. This is obviously not where we're going to go because this will revert, but I'll just show you how to not solve this right now. So we're going to send in 4. This is the wrong solution because it jumped right here, right into a revert statement. I think you got it. Okay, if I put 7, it's also going to revert. Let's try again. And let's put 7. This will also fail. Yes, it also failed because it jumped down to 7. How about we put 8? Well, that's obviously the solution. So if we put 8, it'll go down to the jump destination. So you kind of I just want to make sure you get the point of these exercises and how they look and how they're structured. You start at the top and you just need to read the opcodes one at a time and it'll ask you to send something in so that you end up at the green location. So now I want to call value to be 8 because then my jump statement will read it, jump to location 8, which will be a valid jump destination, and it'll execute the next one, which will be the green one, and it'll stop. So we're going to put 8. There you go. Puzzle solved. Now, as you can see up here, during the solutions, or during the guessing here, it did print a hint for us. It said, hey, this was wrong, but you can copy this and put it in your browser. So let's do that. And it actually copies the particular puzzles opcodes right into the playground which is convenient. That's great. Saves us some time. Another way you can get it if you don't want to guess wrong first, we can play the next puzzle, is you can go into the puzzles and you can just go into puzzle 1, for example, and it'll have the code right here. You can just copy that and put in the playground as well. Okay? But anyway, we're going to not send anything in, and we'll run it without anything. So you see here, this is also replicated over here. It's the exact same as your command. But now you can kind of step through one at a time to see exactly what happens. The stack is 0 because we didn't 0 in. Now it's going to jump to location 0, which is actually back to call value. But since it's not a jump destination, it can't jump there. So that's why the computers are super sensitive around where you're jumping around. It's such a dangerous opcode in general, because you can imagine hackers, like if there was no check on jump destination in the code, they could just jump to wherever they wanted and take control of your code and rewrite things at will. So it's a very dangerous operation, and that's why they safeguarded it with the jump destination. Anyway, we do the next thing. We're going to jump to 0. Boop. It's going to be invalid jump. Now we're going to send in 8, and we can see it go through now. So let's send in 8. We're going to run it. The call value now, you can see on the stack, just the call value opcode took the 8 on the stack. Now we're going to jump. Jump is going to take whatever's the top plate, that's 8, and it's going to jump there in the code. 8 is right down here. It's going to jump here. Boop. We're at the jump destination. That was me making that noise. And then jump to, and then the next opcode is stop, is what I meant to say. And then you click, boom. That's how you complete these. You basically just post it in here, and if you can get to the end without reverting, that's how you solve it. Next puzzle, let's look at it. We got call value. Okay, we're familiar with that. We can send in some value. Actually, let's just play it. So it'll jump to the latest puzzle. Also, I want to show you too that it does store in solutions here. It does store solutions. You can always retrieve what did you send in. For the solution to number 1, we send in a value of 8, and it didn't ask us for any data. In general, it can ask for both, some value to send in and some call data to send in. In 1, it didn't ask us, so it just says 0x. There's nothing. Okay, so just so you know, you don't have to like reclone it or resolve it or anything like that. Okay, so puzzle 2. What does it say? It's a little bit more advanced now. It asks us for a call value. It also asks us for code size, or it like computes the code size rather. It subtracts the 2, and it makes a jump to whatever that number is. That is the subtraction of those 2. So call value will be pushed to the stack. Code size will be pushed to the stack. It's going to subtract the 2. Code size will be at the top of the stack because it was pushed the latest. So it's going to be code size minus call value. It's going to be some value. Jump will take whatever that difference is, a minus b. This is a, this is b. It'll take a minus b and jump there. So we got to make sure that a minus b is 6 because we see that that is a jump destination, and then it'll stop. It doesn't matter that there are these reverts after because the stop will stop the program and we're in the green. So we have to find this island, so to speak, right between these this water here. It's like golf, and we got to get the ball right here. Cool. So what is code size? Let's just understand what are these 2 values. We know call value is whatever we send in, so we have control of this. What is the code size? The code size is, well, you see these numbers to the left, the gray numbers, 0, 1, 2, 3. That's the hex representation, basically of each line in the code, and we'll tell you about the code size. So the point is that the code size here is actually 9 plus 1 because we're counting from 0. So it's 10, right? 10 in hex is A. Okay, great. It doesn't really matter. It's the hex because we're just going to subtract. But it's 10. That's the code size. So we need something that's 10 minus. So it's like it's like 10 minus x has to equal 6. Why 6? 6 is the jump destination. Right down here. Look at this 6. So what is x? Okay, well, let's guess 4. Okay, so we're going to guess 4. It's going to take 10 minus 4 is 6, and we're going to solve it. Done. You see that? Puzzle solved. So that's what happened. And we can confirm. Let's just take one more look at what happens in here. We're going to run this. We're going to have a call value. It's already preset to 4. It's already preset with whatever it like spits out there. It also makes sure to do that. But anyway, we have a call value. Okay, it's going to take 4 on the stack. Code size, well, that's going to be 10. So it's going to be A. It's going to be at the top of the stack. Look at that. A goes to top, 4 below. Subtract the 2. Well, the sub opcode, which we can confirm over here. Go to opcodes. The sub opcode is right here. It takes they always write index 1 is top of the stack. You just confirm, but that's always the case. It says A is the first integer value, B is the second one, and then it does A minus B. So you know that A is the top of the stack. It's obviously important for subtraction which order it is, but the top of the stack is A here. So that's the first one. And then it puts A minus B back on the stack. Cool. So anyway, it'll now subtract and put back. So what's going to be, when I click this button, what's going to happen is it's going to be 6 on the stack, and it's going to be going to code location 3. Right there, so 6. Now it's going to jump, and it's going to jump to location 6 in the code, which is right here, jump destination. And jump destination doesn't do anything except you're just standing there, and it just checks that you got there from a jump. That's all it does. Great, yeah, we did. And then stop, great, it just stops us. That's it, and we solved it. So that's how you do it. That's how you go through these, and you can go to the next puzzle, and some of them gets more and more crazy. So call data size. Now this is the first time you have to send in call data and not a value, but an actual data. So it comes in like this, or 0x something. I think this puzzle behind the scenes strips away that 0x, so I don't think that's necessary, but it's just good to understand it is in hex. It takes the size of this call data, and then it jumps it takes the size of the call data, puts it on the stack, and jump reads it again, just like before, and we need to make that 4. So we need to make the size of the call data 4. So, like, let's try to send in, 2 here. Okay, wrong solution. Let's try to send in 4. Oops. What happened there? Oh, I said no to play again. Okay. Okay, so this is for bytes. Okay, so call data size. Let's do this. Okay. So let's play that one in here. So we can see what happens, okay? So let's do run, call data size here. It's going to be 2. And then we're going to jump to 2, which is wrong, which is revert. So it just behaves the same way, but now we call data size. Before we used value, which was 0, okay? So that's all that's happening. So each of these, remember that we said earlier as well, like each of these is like 2 hex characters is 1 byte. Another 2 is another byte. So this is 2 bytes, so that's why the size is 2. Okay, that's how it works. So yeah, we can play again and then do 0x, ff, and that's it. Okay, so that is 4 bytes. Cool. And then we can play the next one and so on, and we can keep going. And look at this. Now it does call value versus code size. We know the code size is not 10 anymore. It's B plus 1 because we're starting from 0. So it's actually C is the size of the code. That's the code size. We need to say C minus whatever call value we put in. It needs to XOR to a value that is A. Okay, so you can run that math behind the scenes. I'm not going to go through more. I just wanted to show you, I didn't want to make the video too long, but I just wanted to show you what this is, how it works. And when you're done with these puzzles, there are more puzzles that you can go to. So there are, let me go to GitHub. There are definitely more puzzles that you can go to. Let me take a look at my repos. There's more EVM puzzles right here. Here are my solutions. Don't go there. It's a spoiler alert. But this comes from, well, go search for it, actually. I mean, this is public, so you can totally go to my repo, clone it, but I just have all my solutions written out. So don't, spoiler alert, don't. But you can also just go search for more EVM puzzles, crypto or something, and it should show up on GitHub, okay? So, and that's just more puzzles. That's all it is. Cool. So that's really what it is, and it just gives you an idea. Now you might be thinking, okay, fine, I can do these Opcode puzzles, but I still don't really understand Ethereum. I'm gonna put together a video on what it is and how you can kind of see it, but definitely go see some videos also on just the virtual machine. At the end of the day, it's just, especially for Geth, for the Geth implementation, it's Go Ethereum. So it's Ethereum implemented in Go. That's the most common implementation. It's essentially, at the end of the day, it's just this Go code that runs your transaction and everything. This is what is running on the nodes, what the miners are running, everything like that. And when you send a transaction, it just goes to the node's computer. The computer runs this in their Go code, and they just spin up a virtual machine in the Go code, and then they run through the virtual machine. These Opcodes, like I showed you here. That's all it is. So when you call another contract, you call another account, you do whatever you do, just these Opcodes here. So that's why that's why this is just interesting. So knowing about them it just teaches you more about what happens underneath. But we'll do another video where we kind of dive more into the mechanics. But yeah, anyway, get familiar with the opcodes. I'll post some cool links to some nice videos that explains the background. And yeah, that's it. Well, thanks for watching. Like the video, and also, you know, give me a follow. And yeah, I hope that you watch later videos as well. It's one of that transition, something I've been working on. Let me know what you think of the transition of the video format of everything. Thanks so much for tuning in. Let me know in the comments what you like, what you do not like, what you want reviewed, other videos you would like on Ethereum. I'm happy to explain it. We can go very simple. These are more advanced. But yeah, thanks for tuning in. Okay, take care. Bye.